Welcome back. So in this little video, we want to start talking about some ways that we define acids and bases. So there's two basic definition systems. We have what's called the Arrhenius definitions, and these are some of the older definitions. And under this system, an acid is defined as a material that produces hydrogen ion in solution. Now, we'll find out later, or we'll look a little more detail, is that the hydrogen ion doesn't actually exist as hydrogen ions, but it will react with a water to form what is known as the hydronium ion, or H3O+. Under a base, under the Arrhenius system, a base is a material that produces hydroxide in solution. So hydroxide ions in solution. Now it should also be noticed that originally this definition was very structural, and so it had to have an OH ion in the molecule. So one of the issues that this definition system had is that it excluded a lot of the things that today we know do indeed function as bases, like bicarbonate bases and nitrogen bases. So it's one of the things that sort of led to the replacement of the Arrhenius system, at least in functional use. We still utilize this system for an understanding of what's happening in solution. But we have what's called the Bronsted-Lowry definition system. And this uses a definition where we don't look at structure and what's produced, but we look at more of what's happening in the reaction. And so we view an acid as what's called an H+ donor. Now, something we'll refer to later on, but I'll just mention it now, is that in acid-base discussion, or sort of nomenclature, an H+ ion is referred to as a proton. Not the subatomic particle, but we just talk about H+ as a proton because that's all that it really has. An H+ ion is essentially a nucleus with one proton in it because the electron has been lost. So you'll hear this language, and I will use it, books will use it, will refer to a hydrogen ion as a proton. So you might see this definition, if you look under some other source, you might see these definitions defined as a proton donor and a base defined as a proton acceptor. Okay. So Arrhenius, Bronsted-Lowry. So let's look for each of these a little bit more in detail and talk about some specific ideas that these definition systems are useful for. So first we'll start with Arrhenius. And so if we look a little bit at what happens in solution. So one of the things that we still quite often use the Arrhenius idea for is to understand what an acid does when we put it in water and what a base does when we put it in water. So acids, as we said, produce hydrogen ions in aqueous solution. So an acid really is not an acid until it is dissolved in water. So oftentimes, we'll refer to things like HCl, right? Hydrochloric acid is fine, but hydrochloric acid is only hydrochloric acid when it's aqueous. If I have HCl gas, right, it is not an acid, right? It's hydrogen monochloride, right? It is just a binary molecule that is in the gas phase. You dissolve it in water, it releases the H+ ion, now it's an acid. Okay. So if I dissolve HCl in water, I generate a bunch of H+ ions, and of course I have to generate a negative ion as well. So if we generate positive ions, we have to have a negative ion to balance it out. So acids produce H plus ions in aqueous solutions. Now, as I mentioned before, these hydrogen ions don't exist as hydrogen ions, and we will often show pictures and we will use H plus in chemical reactions as a shorthand. But we should always fundamentally understand that when those hydrogen ions are in solution, they exist as hydronium ion. And so that hydrogen ion is reacting with a water, and we're producing the hydronium ions. This is a much more stable ion, and this is going to be the stable form of this ion in solution. Now, as the book notes and other source notes, there are other sort of more complex versions of these, but by far hydronium ion is the most common species that we find there. So we should understand what this means, but again, we will use H3O plus and H plus interchangeably, especially when we're writing out chemical reactions, because sometimes it's useful to use hydronium, sometimes it's just simpler to use H plus ion, so we don't have that extra water hanging around. Now, bases, as the definition says, they will produce hydroxide ions when dissolved in water. So again, right, the real basic properties, they don't have these basic properties until they are a solution. Right? So if I have sodium hydroxide, right, and I dissolve it in water, it is going to separate or dissociate into sodium ions and hydroxide ions. Now, one distinction I'll make here, and I'll go back for a second, is notice when HCl goes into solution, right? HCl is not an ionic compound, right? It is a molecular compound. So it can't just break apart into these ions, right? There has to be a reaction that takes place. This is the reaction. Right? This is called an ionization. And so, in other words, we are reacting to form the ion. So, hydrogen, right, the hydrogen on HCl reacts with water to form the hydrogen ion, because HCl can't just fall apart into ions like an ionic compound has, because the ions are not there. It has to be made, if you will, right, by a reaction. Whereas here, sodium hydroxide is an ionic compound. It can just simply dissociate into sodium and hydroxide ion. And again, these were the only kind of bases that were recognized under the Arrhenius system. Now, when we have an acid plus a base, we get the hydrogen ion or hydronium ion that's generated from the acid, and the hydroxide ion that's generated from the base, combining to give you water. Right? Now, of course, we can't just have the ions combining, because we also have negative ions from the acid and positive ions from the base that are floating around in there, right? So we have the chloride ion in this example, and we have the sodium ion, and from hydroxide, those two ions are going to be shown as combined into what's referred to as the salt, or an ionic compound. Now, almost always this ionic compound is soluble, and so the ions don't actually combine, they're just floating around in the solution. But again, in chemical reactions, we draw them as a species that is aqueous. So this implies that those ions are separated and floating around in solution. And so you'll often see an acid-base neutralization reaction sort of summarized as an acid plus a base gives you a salt plus water. A salt just being another term for an ionic compound. And so this is your classic Arrhenius neutralization reaction, right? Where in the end, you no longer, assuming you have equal amounts or equal moles, I should say, then you will have no hydronium ion left, no hydroxide ion left, and so you make something that is neutral, right, as opposed to acidic or basic. Okay, so that is the Arrhenius definition. Now, as we go further here, we're going to pick up next talking about the Bronsted-Lowry definition system.